Been looking at a lot of pictures, so I'm going to try to make this fairly quick. I didn't do YouTube Friday, but what I did do was this. Right? I asked ChatGPT, can you write about the process of structural engineering like a soap opera? Right? And this is what I came up with. The Pillars of Passion, a structural engineering saga. Isn't that creative? Right? Because I'm into soap operas, like that one that I showed you on YouTube last week, right? My Secret Life of My Billionaire Husband, right? I thought this was pretty interesting. I read through it, and then I was like, "Oh, this is great." I'll post this on our D12 page. You can read through it. I was pretty into it actually, and I said, "Could you give me an image that represents it?" Right? Look at it's what it involves is there's a Grace structural engineering firm, and then someone goes through and alters the plans to make it to just change it, and the other people didn't like the changes associated with it. So like, who did it? Like, who made the changes to the plans? They have lots of puns throughout. Like this first part, the architectural term was charged with the matriarch Evelyn. So Grace Structures, a renowned structural engineering firm known for its innovative designs, like Grace Structures, right? Like the matriarch Evelyn Grace, a visionary engineer, had always balanced the beams of her profession and personal life with precision. But little did she know, the foundations of her world were about to be shaken. Their protege and senior engineer, Damian Steele, known for his unwavering principles and steel frame resolve, discovered the shocking secret. The blueprints of their latest skyscraper, the pinnacle, had been compromised. All right, so then I was like, oh, give me some images of it. I thought this is pretty good. This is my favorite one. Right, it's a secret meeting with a structure going on in the background, but somebody had altered the design. And then what was really cool, I mean, just to show you the power of this thing, I tried to give it to me like a comic book and mess with that a little bit. But then I said, can you give me the script? And so then it put together a script for it, right? Right? The title of the episode, The Blueprint Unveiled, the revelation in the boardroom. It enters Grace Structures boardroom. The boardroom is filled with tension. Evelyn Grace does this stuff. Evelyn comes in and says this stuff. Julia says this stuff. Damien says this stuff. And there's a love connection between like two of these players. And so then that gave me the whole script for the first episode. And I read the whole thing. I was like, oh my God, could you give me the next episode? And so then it made me the next episode. And I kept doing this for 4 or 5 episodes, absolutely engaged with what was happening. So, okay. That's YouTube Friday. I'm just showing. I mean, it is absolutely going to change the world, right? It really is, right? Like so just be prepared to start messing with it, honestly. Okay, I also assigned a homework this week, right? I made it due Wednesday. Why Wednesday? I just wanted to, let's try, right? Let's do it. Let's get into it. Let's dive in, right? Because I want to get started on the next stuff. This is just review. We'll see if I'm a huge pushover in my family. So if you'd be like, oh, are you sure Wednesday? I'm like, well, okay, Friday. But now, but then if I said Friday, you'd say, well, what about Monday? And so now I'm setting it up for kind of next Friday. So here's just a statically determinate truss, right? I will also mention I made these problems, right? Or I found these problems, and I was like, all right, let me see if I can do them. I haven't done structures one stuff in years, right? Like, do I remember how to do a truss that, and do I remember how to do shear mo? I was able to do all of these problems within maybe a half an hour. It took me a little bit of finagling to remember some of the details of these things. But so open it, this was statics, this was mechanics and materials, and then this down here was mechanics and materials. Some things when I did these problems just to kind of set the stage, right? So if you're doing a truss, what's the first thing you do when you're solving a truss? Reactions, right? You got to get what the reactions are, right? So you sum the moments. I think I summed the moments about this point right here, and then I sum the forces in the x and sum the forces in the y, and it tells you what those reactions are. Then you just go, I use the method of joints, right? And so then you just look at this joint right here, and you apply equilibrium to that joint. Then you go to this one, this one, this one, this one, this one. You just work your way across, looking at the joints and applying equilibrium to every single joint. And do you remember doing this? And I provided I did a little drawing of each joint, and I showed the two members coming in, and then you guys did that before, right? And I was able to do it, and by the time you get to the end, it should all close out, right? If you get to the end and you're unbalanced at the end, that means you messed up somewhere along the way. Pretty straightforward. The one thing with this one that got me a little bit, it took me a second, is there's a point where you sum the forces in the y direction, and you're trying to figure out the y reactions on these guys. This is the only one that has a y reaction. Why is that? This one doesn't have it. because there's no member in there. Like the only way you can transfer loads to nodes is through the members, right? Axial loaded members. There is no axial loaded member this direction, and so there cannot be, no load can get transferred in there in the vertical order. So this carries all of 18, 18, and 18 kits. So this is the vertical reaction will be those 18 times 3 right there, because this one can't carry it. I mean, another way to look at it is this is a pin connection, right? And so this thing is just free to flop up and down, and so there's no way for it to transfer a vertical load over here. That was the one thing I got hung up a little bit. I was like, oh my God, I have an extra variable. And then I was able to actually go, oh yeah, there's no way for a vertical load to get transferred into this. Okay? And if you start with that, I just worked my way across, applied method of joints and just some logic, and it worked. This guy, shear moment diagrams, right? I just heard some feedback right here. Including the mathematical expression is the hard part, right? Is like drawing what it actually looks like. It's pretty straightforward, but then actually giving the moment and shear equation at each one. There'll be a shear and moment equation on this side, and then a different one over here because there's a discontinuity there, right? Again, same thing you do. You start out with reactions, and then you go to reactions. You could use whatever method. I did it 2 ways when I did the shear and moment diagram. I did one where like, well, I don't even remember what it's called, but you figure out what the reactions, and a reaction with a downward force will cause a jump down in your shear diagram, and then it's constant as you go across, and then this shear goes up, bumps it up that magnitude, and then goes across, or then it'll decrease over like that. Right? I did it that way, and then applied equations to it by using derivatives and integrals and stuff. The other way I did it was just with method of sections, right, where you can like cut this thing and you have a function of x, and then out pops, and then you apply equilibrium with it. Either way, do your favorite method for doing shear moment diagrams, right? Eventually, both of these things are going to come in heavy. We're going to talk about other ways of solving these things than you covered in mechanics of materials, but right now it's just like a refresher, right? Let's start thinking like structural engineers again. And then this guy right here, right? We apply load P right here. These things displace down, and then it pulls on this. So these two get squished, and then that guy gets pulled, right? The key to this is this thing isn't going to rotate, and so they all undergo the same displacement. Right? You guys did this stuff, right? They all undergo the same displacement, and then all of them have to add up to P, right? And then I give you all those. There's the PL over AE, or AE over L times displacement gives you the P, right? So just a little hint on those things. So apply that and go from there. Cool beans? Right. As of right now, there's no TA or anything. So if you have questions and stuff, come see me, right? That's the way that we're going to do, or ask your classmates and stuff like that. So that's the homework. Like I said, as of right now, it's due next Wednesday. Try to do it. Get started on it. Because the timing of it, we should be ready for like a non-review homework by Wednesday-ish, and I kind of wanted to like get moving. Which is surprising based off of what we've talked about in the first 10 minutes of this class. All right. So let's dive back into our notes. Any questions about that? There is going to be a grade scope set up, right? So I'm going to set up a grade scope, and we're going to submit everything through grade scope. It's the easiest way to handle all the things. And I can give you feedback through it and stuff like that. Okay, so what we were just covering, we were talking about the flow of the course. We're going to talk about structural systems and behavior, types of elements, structural systems, gravity systems, lateral loads. Then we're going to do structural loads, right? This is probably by Monday we'll start all the different types of loads and the load combinations, design philosophies, gravity and weight, lateral loads. I'll introduce this ASC 716. That's what governs all of our loads. And that's kind of the first half of the class-ish. This takes a while to kind of work our way through that. And then we'll get into structural analysis, right? Where we're going to be, moments and shears and axial loads and stuff like that. And we're going to mainly focus on matrix methods, and then we're going to work into structural analysis software, right? We're going to apply, we're just going to draw a diagram in a computer program, and it's going to tell us all those things, right? But it's all based off of matrix methods. Okay, so let's dive into structural systems of behavior. This is very, very, very basic, as if you've never even heard of structures before. We're going to have the main structural elements. So usually when you think of a structure in terms of buildings, right, you have a frame. This is considered a frame, where it has beams, it has columns, it has slabs, it has walls, things of that nature, right? So let's just go through and define, like in a typical frame, the different elements, right? Obviously you've heard of beams, right? These are the beams, right? This is what you've done. You've done the beams a lot in mechanics of materials, right? I mean, they're just transverse loads. They're modeled like this. typically a simple support one. They have transverse loads on them, like that. Right? We apply them. Apply loads like this. All right, they carry loads with bending. By bending. Right? That's the kind of the beams. Right? We've all seen beams before. That's these members, right? Beams that are going across that way, and then this way as well, right? And they're loaded like that. And obviously, those are structural elements, and we have to design those. Right? You could draw a little arrow if you want, but those are pretty straightforward. Right? And there's axial loaded members, right? So these are beams carry loads by deflecting down and stuff like that. But there's axial loaded members, right? By the axial loaded, these might be, I think I have different titles on your notes there, but I think I call them columns and compression members. But there's like, actually there are tension members out there and things of that nature. So I expanded a little bit to talk about axial loaded columns or axial loaded things in general. So that it covers the columns in our frames, right? But then sometimes these things can end up in tension. Another example would be a truss, right? Trusses are axially loaded, right? In trusses, they're called cords, right? Your cords of your truss versus the columns here. But I mean, in those guys, right? They are idealized as this, right, with some sort of roller like this, and then some load on it like this. Right. These axially loaded members. Right. And they show up all over the place. Like I said, they end up as they're columns in these things, right? There's these. There we go. Draw the drawing here. Right. These are the columns, right? These guys are axially loaded as well in trusses. Like I said, they're either called columns or tension. They could be in compression or tension, and then they're considered cords. Right? They also have beam columns. What do you think a beam column is? Very clever name for them. They act like beams and columns, right? They carry loads with bending and axial loads. They carry bending and axial loads, right? We'll talk about systems in a minute here, but these things would be, right, they'd have a load on it like this. Right? Bending and axial load. Those are called beam columns. Very clever name. They're like, oh, they act like beams and they act like columns. What do we call them? Oh, let's call them beam columns. Okay? That happens a lot. We end up with moments and axial loads on them as well. Right? The other element would be a flat plate. Okay, it's like the technical term for that. And you can load plates either in plane or out of plane is what they're called, right? In plane or out of plane. So loaded out of plane would be a slab. Let's see if I can draw a slab for you. Nope. Did you see what it did? It turned it from... All right, let's try again. A trapezoid. Uh-oh. That ain't gonna work. Fuckers. One more time. What'd you do today? Well, the professor tried drawing a slab. Oh, I got it this time. I used the squares in the... That's a good start. I have graph paper there. I might as well use the graph paper. Right? Right? Something like that, right? And what I mean by loaded out of plane, meaning like here's the plane of the wall, but I'm going to load it down like that. Like a floor, right? A floor would do that. This thing would deflect like this, right? It could deflect a couple different ways. Right, there's this thing called one-way bending or two-way bending, but if you applied a load to the top of this thing, it's going to deflect down. That's kind of how I sketched in red right there. Right? So these are floors. Floors or slabs is another way to look at it. Right, so those are easy to spot up here, right? Just these floors. Right? That's considered, or these plates, right, or these slabs are considered a structural element. And that's actually something that we have to design. I should also point that out. Each of these things we have to design, right? Eventually, we're going to have to design the beams, the axial loaded members, the beam columns, and then the plates, right? So the whole design would be designing every one of those things, okay? This next one here would be flat plates loaded in plane. And what I mean by in plane, see if I can draw another picture here. Draw it up on its side. Oh, I'll try the same thing I did last time. No. Anybody else have trouble like envisioning what it looks like in like an isometric drawing? That's what I've tried to do, is draw isometric drawings. Oh my God, I nailed it. Okay. Loading it like this. Right, the ground is like this. Oh, the ground's down here, right? The support there. And you're loading it in plane, right? So instead of pushing on it this way, we're pushing it along like that in plane. Like, why would we do that, right? Why would you load a plate like that? Well, it's part of the lateral system. We'll talk about the systems in a minute. Like, there's a gravity system and a lateral system. So if you push down on it vertically or you push on it horizontally, there's different components. These things are called shear walls, right? This is a way that we can load it. The other way we can load it, like an in-plane load on a wall, would be, let's see if I can do this. Or you can in-plane load a plate. Oh my God. Would be applying a load like this. Like that, okay? So if you had the same type of plate, you can also apply loads in that direction. Still, again, in the plane that the wall is taken up, okay? Over here on the left, right, this is what, like I said, we'll see in a little bit, but this is called a shear wall. Okay? When we talk about plates like that, and this is called a diaphragm. Maybe it'll let me write that. Floor diaphragm. When it's loaded like this, it's called a shear wall. If it's loaded like this, it's called a diaphragm. And we'll talk about those in a little bit more detail later, but back up to our structure up here, right? These guys right here, right? Even the elevator core that they have in here, those are considered shear walls, right? Because you can imagine if you came in and pushed this thing from the side, say wind hitting the side of the structure, right? Obviously there'd be cladding on the outside, but the wind hitting the side of this thing, those loads have to get are resisted. These lateral loads are resisted by something. One of the things that we resist it with is walls, right? It's actually a very common way, especially in housing, right? My house's lateral system is shear walls, right? Is what we put in to keep it from tipping over. And so you can imagine how these things are loaded. There's a big old point load that'll come in on each floor, right? That'll come into the side of these walls. And so that'll be a wall or a plate that's loaded laterally, okay? The other one that I drew, right, was a plate being loaded like this. Same idea. If you hit the structure with a wind load from the side, somehow that load from the side has to make it into these lateral resisting systems, and it does so through the floor, through the diaphragm, right? The load will get transferred into this floor, and then that floor will be loaded from the side, and it'll have to transfer the loads into these into the shear walls, right, or whatever your lateral system is. Okay. Those are your main really, all of structural engineering involves these basic elements. elements. There's no real other elements, right? So when you talk about the design of a structure, you're talking about the design of beams, the axial members, the beam columns, the flat plates in terms of like the floors and the slabs, and then the shear walls or the diaphragms. And that's it, right? So all of structural engineering is after we're gonna talk about getting the loads that you design. Structures 2 says, all right, how do we design these things, right? And then all those other classes that I showed you were all about how you go about designing these different things out of all the different materials, either concrete or steel or wood or masonry, right? It's all about those designs. But these are all the basic elements. Right? The truss is made up of simply all axial loaded members. There's no other elements made in there. Right? I lied a little bit. There's not only it's designing these things, right? Also designing the connections, right? You have to connect all of these different structural elements, and that's the other part of structural engineering is how do you go about connecting all of these things, all these elements? Because there's big forces that come in those connections. Questions about that? Those are the types of elements, right? Those types of elements go in to making a system. A system would be just a system of elements, right? The elements, all the things we just talked about before, but then how you confine them and connect to them and stuff like that, they all behave differently, right? My notes are on my phone, by the way, so it's not like I'm not texting up here. Sometimes I'm texting, but not right now. All right, and so let's talk about the different systems. Again, I mentioned this before, there's actually 2 main types of systems, a gravity system and a lateral system. The gravity system, right, has to do with supporting gravity, right? Well, what are the gravity, right? It's the weight, right? Rate of structure and occupants, right? Or occupancy loading, not just occupants, but right? It's all weight, right? It's the pull of gravity on the structure. Obviously, this is the key one. Right, back in the day, that's all people cared about, right? So your structures downtown, right? When the structural engineers back in the day were like, hey, we just really care about weight because that's the most immediate thing that you see, right? And then, oh, by the way, there might be some wind or something like that. But nowadays, they're equally as important, right? You design for gravity and lateral systems, right? And that's why our structures stand up in earthquakes and stuff like that. So then what are the systems for supporting gravity? Obviously, there's the truss, right? Right. You've seen these before. This is statics. You don't do anything in mechanics materials with these, right? These are all just going back a couple semesters. But this is a key one, right? And this is actually how they start all structural engineering classes is the discussion of trusses and the analysis of trusses, right? And what's nice about them, right, is you only put material where you need it, right? You can make a whole triangle and it would be stronger than a truss. But we're just saying, like, well, how can we optimally use our materials? Well, we'll make them spread out as much as possible. Give them the biggest moment of inertia possible. If you spread them out like this, you can carry more load. It's like making a deeper and deeper beam, right? And so you do so with trusses, and you only put elements where you need to need elements. I did a big research project a couple years ago. There's this program there's this methodology called topology optimization, where you model these things in finite elements, and then you say, hey, analyze this thing and do an optimization on it. This whole theory behind it where like the computer's going through, and it's actually based off the theory of evolution, where if you believe in that sort of thing. No, but the theory of evolution where you start out with some design and then or some initial deal, and then there's rewards and penalties as you go along, and it goes through thousands and thousands, if not millions of iterations, and it evolves, and there's rewards, like if you do something right, and it basically evolves into the optimal structure, right? And so we did this big deal with a grad student of mine, and she went through and put in all these parameters, and we said, oh, this is gonna be magnificent, we're gonna put it in, and we're gonna let it run, and see what it comes up with. And we went through, and what it came up with was a truss. And you're like, oh shit, well this isn't publishable, right? Like, except for the concept of, oh, hey, by the way, trusses are pretty close to an optimal design of something, right? And you'll learn about this as you go, the more you go into structures. The most efficient way for a material to carry a load is through axial loads, right? It can carry axial loads really, really well. once you start bending things, when things get bent, it's less efficient. So if your really efficient way of carrying it is with trusses, right? So the whole point, trusses are sick, right? There's these types of trusses, and then this actually, a floor joist, open web floor joist is also a type of truss. You can see these. These things are all over the place, right? If you go into like big gymnasiums and stuff like that, if you look up, you'll see these floor joists all over the place. Right? It's very. I'm certain that this, maybe not this building, but some of the newer buildings all have these open ways because this is, you don't have material where you don't need it. The key parts are these parts, and then these are just used to kind of hold them together and transfer loads between them. So we'll talk about analyzing these trusses. The other most common is a frame. Right? These are our typical frames. They're called and the frames consist of beams and columns, right, and plates, right. So these we already looked at these, but these are the typical structural systems that we'll see, right. And we're going to talk, what we're going to build up to is like, well, how do the loads get transferred around in a frame, right? They start out in the plate, then they go into the beams, and then they go into these things, we're going to call these things girders, right? When beams feed into, they get feed into those girders, and then those girders transfer over. That's called load, you're tracing the load path, and load paths. So we're going to talk about load paths, right? Because all buildings have these load paths associated with them. But this is the other type of system, is a frame. Right? They consist of, you might as well just write some stuff down every once in a while. Right? They got beams, they've got columns, they got plates, or slabs, floor joists, and or floor joists. Right, and then sometimes, we'll just say girders for now. They get used. Girders and beams get used interchangeably. Usually, what you call a girder is something that has beams framing into it. So you got these beams going across, and the slabs sitting on those, and then those beams transfer the load into these girders, which will come in as point loads, right? And so, usually that's what it means. If you hear the word girder or the word girder, that's what it's talking about, which is a very word to say. I just said it like 5 times in a row. Girder, girder, girder. No? Not weird, but it is weird. But then like in a bridge, all the beams are just called girders in a bridge. So there's a lot of interchanging stuff. In a building though, girders usually means that things are being transferred into it. Okay? Another type of structure would be our cable, tension structures, right? They basically draw like an idealization of that. Right? You can imagine if you had a cable strung between 2 points and applied a load in the middle of it, right? That's structurally stable. Right? That's a structurally stable thing. It's kind of weird, but it is structurally stable, and it's carrying the load with axial loads. They're actually very efficient. Cable structures are. You pull down, it's just all axial loaded cables, which is pretty crazy. I mean, just to put things into perspective, right? When we'll learn about this in structures too, but you guys learned about yield stress and things like that, and right, you did, right? And maybe you didn't ever like fully grasp like how strong, like steel, for example, right? Or let's start with concrete. Concrete can carry 4,000 pounds per square inch. That's a standard 4 KSI. Right? That's axially loaded concrete. You squish it. 4,000 pounds per square inch. So you take a square inch, about like that. You can put 4,000 pounds of force on that before you fail like normal weight concrete. Isn't that crazy? Like 4,000 pounds. Just a little guy like this. I mean, that's a pickup truck. Right? I mean, let's see, but a standard pickup truck is about 5,000 pounds, just under that, right? It's very common to have 5,000 psi concrete too. So that's 5,000. You put a whole pickup truck on this 1 square inch of it. Great. This is how strong steel is. Do anybody remember what the yield stress of steel is? Don't remember. You ever heard of that? 50 KSI. 50 KSI. 1 square inch of steel can carry 10 pickup trucks. 10 pickup. You could hang 10 pickup trucks from 1 square inch of steel. Not amazed? You should be fucking amazed, right? Like this is, for God's sakes, it's 1 square inch. You have 50,000 pounds, 10 pickup trucks hanging. Maybe we just need to get some pickup trucks and start hanging them, right? And just show you, like, look at this, right? The steel you use. So I teach another class called pre-stressed concrete. In pre-stressed concrete, you use a special steel for these tendons for squishing the concrete. This is what the ultimate stress of a pre-stressed tendon is. That type of steel. 270 KSI. But just making me a wow. Like, you should be like, wow. 270. I can't do that math. 270 divided by 5. What's 270 divided by 5? Somebody? Get the calculator. You should be able to do it. I guess 60. 55. Oh, close. 55. 55 pickup trucks could be supported by 1 square inch of a pre-stressed tendon. Holy shit, right? It's magnificent. It's really cool. So then that's what we're talking. That's how much you can carry in tension. Once you start bending it, it's a lot less. But then this, right? So these are really good. They're so good to just carrying stuff in tension. So everything's a tension. I mean, that's why we make these guys out of it, right? This is a tension structure, right? This is the Golden Gate Bridge. I've been on the Golden Gate Bridge, and it is really cool. I walked out halfway, right about there, and then came back. It was pretty cool. Has anybody else been on a big suspension bridge? It's sick, right? It's really sick, right? But that's the only way you could get that kind of spans. You couldn't do this with girders. Just plain old girder span across. There's no way you could have that thing. Like the longest bridge in the world, I think it's outside of Turkey. And it's the mid-span between these two supports is like 1.25 miles in between the supports. Right? Isn't that phenomenal? I couldn't run across it. Right? I'd have to stop about halfway. It's also got a little arc in it. I'd have to stop about halfway, take a little break, and then go from there. Well, the other one about these types of structures, this is off topic but cool stuff, is the Brooklyn Bridge. Anybody been across the Brooklyn Bridge? Right? It's phenomenal. So cool. Guess when the Brooklyn Bridge was made? 1906. Yeah. Within 5 years after the Civil War. Like, isn't that fucking crazy? Like, they were building shit like that. I read a book recently, had it read to me. It was listen to audiobooks. I can't read. I listen to audiobooks, and I was listening to audiobooks. It's called The Great Bridge, and it's about the engineering behind the Brooklyn Bridge, and it was phenomenal. It could be considered by some to be very boring, but to a structural engineering professor, it was very entertaining. Like, especially how they did the foundation. They did these big caissons, and they did pressurized thing. They'd go underneath it, and then they basically would have this little bell that was isolated from the water, and then it'd be pressurized, and they're down underneath it, and they were just people in there just shoveling underneath it, and then as they shoveled underneath it, the little bell just continued to sink every time they dug out, and then they started using dynamite in it because they started getting into, and so there was like blowing stuff up and then going down and doing it. Hundreds and hundreds of people died in the construction of Brooklyn Bridge. It was incredibly, incredibly unsafe. But cable or tension structures is they're really cool. A very efficient way to carry loads. And if it wasn't, you couldn't do these big, large spans and stuff like that. These guys, arch or compression structures, right? I want to come back up to this really quick. This thing would cause, right? This would cause these big reactions like this, right? Right? It would pull on those things. You have to resist that. These compression structures are the opposite, right? Where it's going like this. I would have to have a support on this end, right? And you apply a load like this, right? And this would cause, reaction forces out like that. You call that thrust, I think is what you call that. Tried to write. It would push out like that. And so examples of that would be, this is that, the Hoover Dam bypass, right? This is a compression structure. You push on it, right? And then this arc is actually fully axially loaded, right? You look back at some old images of like some of the first bridges that they did back in the day. They're still standing up. Right? They stack blocks, right? They stack these blocks up like this and apply load. And the way it works, right, as long as you resist this thrust, right, as long as you provide a reaction there to resist that thrust, that member becomes fully axially loaded, which again is very efficient. Carrying things axially is very efficient, right? Another perfect example would be our dome here. This is our dome under construction. Right? It's pretty cool. Back in the day, again, look at the era that it was built, right? I think it was built early 60s, right? So they have these big timber that's made of timber. It used to be the largest timber dome in the world. We'd be talking about this? Yeah, right here in our backyard. And then the Tacoma Dome took care of it, took it out, right? And so you have, in this case, you got all these members coming up, and you got a big compression ring. Because you imagine if you push down on the top of this, that compression ring, that ring would go into compression. And then everything on the outside, you got this tension ring that's resisting it that way. But this is, all these members are loaded in compression. I can't help it. I gotta show you some pictures. This is Brick Breeden. Just in case why they call it that. It's this guy. He used to be a basketball coach. They had the world's middleweight championship in there. What was it? 1960. They had that. It was. I don't know those guys. All right, Gene versus Joey. Just different pictures of the campus. There's Romney over here, right? And there used to be a field behind here, and actually. That's across the street, right? And so right here, like if you look out in front of the new building and stuff, there's like a little archway thing that's commemorating that's where the football field used to be. If you see that and you're like, oh, what is that thing that's out front? And it's just a commemoration of this old football field that used to be right there. It's not there anymore. Old basketball game in there. Under construction. There was one thing in particular I wanted to show you. See, now it's a little bit more advanced now that it's not mules and stuff. They have this guy with all cables and stuff. It's still pre-hydraulics, right? It's all cable-based as it's digging and stuff, but at least it's a piece of equipment. And it's being constructed. Pretty cool that it's like out in the middle of Montana. So this is really cool. So that's it. Before everything's actually up into place, it's not stable. Right? Like you have to support these things. And so what they did is they just went down and cut down a bunch of big tall trees and then spliced those trees together, right? So that they could reach up and hold on to the thing until they got out there. And even once they got out there, then they still had to hold on to it, and then they had to bring in all the other ones. All of them have to be in place. And the lateral supports, right? Because remember what would happen if this thing twisted. The whole thing's coming down, right? And so you had all those lateral supports. They had to have those things in place. And then they had to have all these things there until you got that in the lateral supports. Once they got it, then they could take down these timbers, right? Guess how they took down the timbers? They sent a guy out there, probably an intern, right, with a chainsaw. That's exactly what it is. It went out there with a chainsaw. It started cutting them down, and they would drop and then fall over, right, as they went along. And they were just like, they were probably in there just like, oh, God. They should have sent the real engineer out there, right? Back to the Roman days, right? Like when you pull the scaffolding off to make sure it's going to stay. And you imagine doing that? Just boom, and the thing would just start, it would sink every time one of those things would be removed. And so on the outside, there's a big tension ring that goes around the whole outside. That spans all the way around outside, and the compression ring up at the top. You kind of see the tension ring there. And then, there was an accident, right? That crane, it wasn't supposed to be like that. It fell over, right? It fell over. A big part of it fell down. There's a little thing of the accident. Pretty Wild West back then. I mean, not as Wild West as, but also kind of Wild West. Like, look where it's built. It's in the middle of a field, right? But where I got these pictures from was the architect on the project. When I first started here 18 years ago, the architect was still alive. He's since passed, and he came in and gave a presentation to the class of like the design. So all these pictures came directly from him. steam tunnel looks a little bit different on that. Okay. And we were doing pretty good, and then now we're back to not so good. So compression to arches and structures, right? Okay. So all this stuff is gravity, right? This is the weight of the structure. You're applying gravity loads to this. These are the main types. We're going to primarily focus in this class at the beginning on these two, right? Frames and trusses. If you go to be a real structural engineer, this is where you're going to live mostly, right? I think very rarely will you do a tension structure or an arch. Right? Those are usually specialized applications, okay? So for lateral loads, okay, so this has to do with, lateral loads or wind and earthquake. We said that a couple of times before, right? Right. Wind and earthquakes. Right, and then there's other things too. We talked about earth pressure and etc. Right, the fact, backfilling a foundation, or if you have one of those walls called the retaining wall. If you have a retaining wall, those things get laterally loaded. But in terms of buildings, we're talking usually more wind and earthquakes. So there's the main types of lateral systems that are out there, okay, that you will typically see. There's a bunch of other ones, so these are just examples. One is a moment frame, okay? The moment frame is pretty common. They have moment frames all over Norm Asbjornsen, right? Those are, the primary lateral system in Norm is our moment frames. And the other thing I want to point out, let's go here. I keep forgetting to say this. I'm going to forget to say it by the time I'm done drawing here too. Right? So this is the real thing, right? This is a moment frame. This is the real one, right? But then I don't, when I go to model it, I don't draw it like this. I draw it like this, right? And this is called an idealization. I have a topic on this later, but I want to point out it's the first time we see it here. But it's called an idealization. This is really what it is, but I'm going to pretend it's these lines, right? And so the way I'm going to model it is lines, right? These are actually called line elements when you get defining element analysis and stuff, but that's an idealization of it. The way that moment frame, if these were pinned connections, we're going to talk about connections in a second. If these are pinned connections, this would be pretty unstable, right? But if you have a rigid connection, it's easy for me to do, hard for you to do. I'm going to change the support condition to make it really unstable. If I put a pin underneath it here, it's fine if you have the other one. I'm just trying to demonstrate. So if these are pins right here, pins mean, again, I'll talk about this in a second, it just means that it can't support a moment, right? It'll only support X and Y direction. And so if that was a pin connection, that was a pin connection, these are pin connections, this thing's unstable. If I went to push this thing from the side, these would just rotate, these would rotate, and the thing would come down, right? To make this thing stable, I would either need to make these things fixed down at the bottom, how I originally had it drawn, or I make the connection between them rigid. I usually kind of draw it maybe like that, and say that we have a rigid connection here. I'll define what that is in a second. Right? If I have a rigid connection, then this thing is stable. Right? If I go to push on it from the side, these things stay at 90 degrees. If those stay at 90 degrees, it's stable. You can't push this thing over. Well, you can. It'll move, but it won't just flop over. It won't be unstable. And so we load this thing up from the side. So, like I said, you'll find these, and this kind of comes from the architect. If you're like, the architect I want a completely open floor plan. I don't want to see anything. I just want to be able to have obviously lateral resistance. A wall isn't going to work. But this moment frame will work really well because there's nothing in between, right? You have a big old window here and stuff like that, and it would be stable, right? The way it would deflect, right? It would go like this, right? And then it would go something like this, right? And then over here it would deflect like this, something like that. Right? You push it from the side and it would deflect. But these things, I didn't draw it right. This would be held at 90, right? If you drew that right, those guys would be held at 90. As they went across. So that'd be a moment frame. That's a very common lateral system that you'll see in structures. Like I said, Norm Asbjornsen, its primary lateral system in one direction at least is these moment frames. Okay. The other one is the brace frame. Right? Again, very common. Very common. Right? And that's these big crosses going across like this, right? And that is all pin connections. Oh, this black. All right. Like I said, if you did this, right, you kind of put a dot here just to show these are like pin connections. Right, this in itself would be unstable, like I mentioned before. But if I put in a brace that goes across like this, right, now this is stable, right? Because if I push this thing from the side, this member is going to go in compression, this member will go into tension, right? And then that will prevent it from being tipped over, right? And that's the whole point of these lateral systems, is to keep it from tipping over. Right? So these are pin connections. I mean, it's also that's a truss, really, right? That's a truss. I mean, it behaves the same, right? Pin connections all over the place. Everything is pinned. Right? But that sucker is stable, right? This guy would go into compression. This guy go into tension. What do you think? Usually when you do design, you often just design for the tension carrying the load. What's wrong with this side? Like, why wouldn't I take into consideration the compression on that thing? What happens to structural elements that you apply large loads to if they're really slender? The buckle. Right, so oftentimes when they push on the side of this one, they don't even count that one because they're usually really slender, right? These are all loaded in axial loads, so they can be really small because they're really efficient at carrying loads axially. And so if this is just like a bar going across, and then you put that thing into compression, it'll buckle. It'll buckle, and it can't carry any loads when it's buckled, but the tension side will carry it. So oftentimes when you design these things, you just worry about the tension. You assume this guy carries everything, and this guy doesn't carry anything. But you can beef it up and make it carry tension. So there's you can see these things. You see these all over the place. The old gym used to have these things. You just see them all over the place. These big lateral braces all over the place to support things, right? And that's a really common one. Which one do you think is more stiff? Which one do you think would deflect the least under a load? The brace frame, yeah, because it's all axial loaded, right? Axial loaded is really efficient. And so this guy is like 10 times as stiff as this guy. Right? This guy deflects a lot, right? Because it's bending, right? It resists those loads with bending. This one resists it with axial load, right? So this guy is way more stiff, right? And then we'll talk about the last one is shear walls, right? You just put walls in there, which your building has anyway, and you use them as a structural component to resist the lateral system, okay? Then we'll get into types of connections next time, a little more idealization, and then start talking about load paths as they move through. All right? Break. Have a good weekend. Grab some more cookies as you go out.
I've got a theory for why Ramen and Montana Hall are.
What is it?
So, see, when you're walking towards Montana Hall, you want to walk towards, like you